Today we're diving into the world of simple linear regression. This statistical method is one of the most fundamental tools in data analysis, helping us understand relationships between two variables. Whether you're a student, a professional, or just curious about data, grasping this concept will open doors to deeper insights. We'll start with the basics, explore how it works, and see why it's so widely used. By the end, you'll have a solid understanding of what simple linear regression is and how you can apply it in real-life scenarios. Simple linear regression is a statistical technique that models the relationship between two variables by fitting a straight line to the observed data. One variable is considered the predictor, or independent variable, while the other is the response, or dependent variable. The goal is to find the best fitting line that predicts the response variable based on the predictor. This method is widely used because of its simplicity and interpretability. It's the foundation for more complex regression techniques and is a great starting point for anyone new to data analysis. Let's break down the key components of simple linear regression. First, there's the independent variable, often called x, which is the input or predictor. Then there's the dependent variable y, which is the output or response. The relationship between x and y is modeled with a straight line described by the equation y equals a plus bx, where a is the intercept and b is the slope. Understanding these components is crucial for interpreting regression results and applying the method correctly. Regression line is the centerpiece of simple linear regression. This line represents the best estimate of the dependent variable for each value of the independent variable. It's calculated so that the sum of the squared differences between the observed values and the predicted values is minimized. This approach, known as the least squares method, ensures the line fits the data as closely as possible. Visualizing the regression line helps us see how well our model captures the relationship between variables. Slope of the regression line, often denoted as b, tells us how much the dependent variable is expected to change for a 1-unit increase in the independent variable. If the slope is positive, it means there's a direct relationship. As x increases, y increases. If it's negative, the relationship is inverse. As x increases, y decreases. The magnitude of the slope indicates the strength of the relationship. Interpreting the slope correctly is key to making sense of your regression result. Intercept, represented as a in the regression equation, is the value of the dependent variable when the independent variable is 0. It's where the regression line crosses the y-axis. While the intercept may not always have a practical interpretation, especially if a value of 0 for x isn't meaningful, it's an essential part of the regression equation. Knowing the intercept helps you make predictions even when the independent variable is at its baseline. Least squares method is the mathematical approach used to find the best fitting regression line. It works by minimizing the sum of the squared differences between the observed values and the values predicted by the line. This ensures that the overall error is as small as possible. The least squares method is widely used because it's straightforward and provides reliable results, making it the standard technique for fitting linear models. Calculate the slope in simple linear regression. You use a specific formula that takes into account the covariance between x and y, as well as the variance of x. The formula is slope b equals covariance x y slash variance x. This calculation tells you how much y changes for each unit change in x. Understanding this formula helps you see the mathematical foundation behind the regression line and why it fits the data the way it does. Once you have the slope, calculating the intercept is straightforward. The formula is intercept a equals mean y b mean x. This means you take the average value of y and subtract the product of the slope and the average value of x. The intercept anchors the regression line on the y-axis, ensuring it best fits the data according to the least squares method. Visualizing simple linear regression involves plotting the data points on a scatter plot and drawing the regression line through them. This visual representation makes it easy to see the relationship between the variables and how well the line fits the data. It also helps identify any patterns, trends, or outliers that might affect the analysis. Visualization is a powerful tool for communicating your findings to others. Interpreting the results of a simple linear regression involves looking at the slope and intercept, as well as the overall fit of the model. The slope tells you the direction and strength of the relationship, while the intercept provides a baseline. You'll also want to consider how closely the data points cluster around the regression line, which indicates how well the model explains the variation in the dependent variable. Residuals are the differences between the observed values and the values predicted by the regression line. Analyzing residuals helps you assess how well the model fits the data. If the residuals are randomly scattered around 0, it suggests a good fit. However, patterns in the residuals may indicate problems with the model, such as nonlinearity or outliers. Checking residuals is an important step in regression analysis. Simple linear regression relies on several key assumptions. These include linearity, the relationship between variables is linear; independence, observations are independent; homoscedasticity, constant variance of residuals; and normality, residuals are normally distributed. Violating these assumptions can affect the validity of your results. It's important to check these assumptions before drawing conclusions from your regression analysis. Linearity means that the relationship between the independent and dependent variables can be described with a straight line. You can check for linearity by plotting the data and looking for a straight line pattern. If the relationship is not linear, simple linear regression may not be appropriate, and you might need to consider other models or transformations. Independence means that each observation in your data set is not influenced by any other observation. This assumption is crucial for the validity of regression results. If observations are not independent, such as in time series data, you may need to use specialized techniques or adjust your analysis to account for this. Homoscedasticity refers to the assumption that the variance of the residuals is constant across all levels of the independent variable. In other words, the spread of the residuals should be roughly the same no matter what value x takes. If this assumption is violated, it can lead to inefficient estimates and affect the reliability of your conclusions. Normality assumption states that the residuals or errors should be normally distributed. This is important for making valid inferences about the regression coefficients. You can check normality by plotting a histogram or a QQ plot of the residuals. If the residuals are not normal, it may affect hypothesis tests and confidence intervals. Outliers are data points that are far from the regression line, while influential points are those that have a large impact on the slope and intercept. Both can distort your regression results. It's important to identify and consider these points when analyzing your data. Sometimes, removing or adjusting for outliers is necessary to get a more accurate model. Goodness of fit measures how well the regression line explains the variation in the dependent variable. The most common metric is r-squared, which ranges from 0 to 1. An r-squared value closer to 1 means the model explains most of the variation, while a value closer to 0 means it explains little. Understanding goodness of fit helps you evaluate the effectiveness of your regression model. R-squared, also known as the coefficient of determination, quantifies the proportion of the variance in the dependent variable that's explained by the independent variable. For example, an r-squared of 0.8 means 80% of the variation in y is explained by x, while a higher r-squared is generally better. It's important to consider the context and not rely solely on this metric. While r-squared is useful, it has limitations. It doesn't tell you whether the regression model is appropriate or if the relationship is causal. A high r-squared can occur even if the model is misspecified. Always use r-squared alongside other diagnostic tools and consider the underlying assumptions before drawing conclusions. Hypothesis testing in simple linear regression helps you determine whether the relationship between the variables is statistically significant. Typically, you test whether the slope is different from 0. If the test shows significance, it suggests a real relationship exists between the independent and dependent variables. P-value is a key result from hypothesis testing. It tells you the probability of observing your data if the null hypothesis is true. A small p-value, typically less than 0.05, indicates that the relationship between the variables is statistically significant. Interpreting the p-value correctly is essential for making sound conclusions from your regression analysis. Confidence intervals provide a range of values within which the true regression coefficients are likely to fall. For example, a 95% confidence interval means you can be 95% confident the true value lies within that range. Confidence intervals help you understand the precision and reliability of your regression estimates. Once you have your regression equation, you can use it to make predictions. By plugging in a value for the independent variable, you can estimate the expected value of the dependent variable. This predictive power is one of the main reasons regression is so widely used in fields like business, science, and engineering. Let's look at a practical example. Suppose you want to predict sales based on advertising spend. By collecting data on past sales and ad budgets, you can fit a simple linear regression model. The resulting equation allows you to estimate future sales for any given advertising budget, helping you make informed business decisions. Another example is predicting student grades based on hours studied. By analyzing the relationship between study time and exam scores, you can use simple linear regression to estimate how much a student's grade might improve with additional study hours. This approach is useful in educational research and planning. Simple linear regression can also be used to predict temperature based on time of day. By collecting temperature readings at different times, you can model the relationship and forecast future temperatures. This method is commonly used in weather analysis and environmental studies. While simple linear regression is powerful, it has limitations. It only models linear relationships and can't capture more complex patterns. It's also sensitive to outliers and assumes all key assumptions are met. For more complex data, you may need to use multiple regression or other advanced techniques. Simple linear regression isn't suitable when the relationship between variables is not linear, when there are multiple predictors, or when the assumptions are violated. In such cases, consider using other statistical methods like polynomial regression or multiple regression to better capture the complexity of your data. Multiple regression extends simple linear regression by including more than one independent variable. This allows you to model more complex relationships and account for additional factors. While it builds on the same principles, multiple regression introduces new challenges and considerations, which we'll explore in future lessons. When using simple linear regression, always start by visualizing your data and checking assumptions. Clean your data to remove outliers and errors and interpret your results in context. Remember, regression is a tool to help you understand relationships, not just a formula to apply blindly. There are many software tools available for performing simple linear regression, including Excel, R, Python, and SPSS. These tools can quickly calculate regression coefficients, plot results, and check assumptions. Choosing the right tool depends on your needs and familiarity with statistical software. Common mistakes in simple linear regression include ignoring assumptions, misinterpreting results, and overfitting the model. Always check your data, validate your model, and be cautious about drawing causal conclusions. Being aware of these pitfalls will help you use regression more effectively. Using regression responsibly means being transparent about your methods and acknowledging limitations. Avoid manipulating data to get desired results and always consider the ethical implications of your analysis, especially when making decisions that affect people or organizations. Effectively communicating your regression results involves more than just presenting numbers. Use clear visuals, explain your findings in simple terms, and highlight the practical implications. Good communication ensures your audience understands and trusts your analysis. Simple linear regression is used in countless real-world applications, from predicting housing prices to analyzing scientific experiments. Its versatility and ease of use make it a go-to tool for researchers, analysts, and decision-makers across many fields. In business, regression analysis is used to forecast sales, optimize marketing strategies, and evaluate financial performance. By modeling relationships between key variables, companies can make data-driven decisions that improve outcomes and drive growth. Scientists use simple linear regression to analyze experimental data, test hypotheses, and uncover relationships between variables. Whether in biology, chemistry, or physics, regression helps researchers draw meaningful conclusions from their data. In the social sciences, regression is used to study relationships between factors like income and education or health and lifestyle. By quantifying these relationships, researchers can inform policy and improve social outcomes. Engineers use regression to model system performance, predict failures, and optimize processes. By understanding how variables interact, they can design better products and improve efficiency in manufacturing and operations. In healthcare, regression analysis helps predict patient outcomes, evaluate treatments, and identify risk factors. By analyzing medical data, healthcare professionals can make more informed decisions and improve patient care. To sum up, simple linear regression is a powerful tool for modeling relationships between two variables. By understanding its components, assumptions, and applications, you can use it effectively in a wide range of fields. Remember to check assumptions, interpret results carefully, and communicate your findings clearly. If you're interested in going further, consider learning about multiple regression, logistic regression, and other advanced techniques. Building on your understanding of simple linear regression will help you tackle more complex data analysis challenges in the future. Thanks for joining this journey into simple linear regression. With these fundamentals, you're now equipped to analyze data, make predictions, and draw meaningful insights. Keep practicing, stay curious, and continue exploring the world of data analysis.